Welcome, everyone. I am so glad to have you here. Welcome to OLLI Extra. As you just heard, 6 states are working together to bring you some incredible programs this summer. We are so glad to have you join us from South Dakota, North Dakota, Wyoming, Montana, Minnesota, and Iowa. A couple housekeeping notes. Please keep your microphone on mute during the session. If you have any questions, save them for the question time. Or if you're like me and I forget what my questions are, I put them in the chat and we'll be monitoring the chat so we can go back and check on those. We'll do our best to get all of the questions answered. And we respect the time that our instructors are giving us, so we do plan to finish on time. Once in a while, an instructor will say, I'll stick around longer for extra questions, but we want to respect Jerry's time today. If your questions are not answered, email us and we'll forward them to Jerry. Our email, as you probably already know, is olli@usd.edu. We are going to post a survey at the end of the program. It'll be in the chat. Please take a minute and click on that survey before you leave the Zoom meeting and tell us how we're doing. Thank you again for joining us. And now I'm going to introduce Bobby, who is going to introduce our speaker, Bobby from Montana.
Hi, everyone. Thank you. I just want to echo the thank yous for at least here it's a gorgeous morning. So for dedicating your morning to join us. And I'm the director for OLLI at Montana State University in Bozeman, Montana. And thanks to Thea, we were invited to join this fun collage of OLLIs this month. And I have the pleasure of introducing this speaker that happens to share the same last name as myself. We are related, although I still have hair and it's a little longer. Gerald has lost most of his hair at this point and it's more gray than mine. But so Gerald Geise, who happens to be my father, is graduated from Montana State University with a degree in chemical engineering. I won't mention what year, but it was a while ago. He spent his career in the nuclear industry as an operations manager for the largest nuclear reactor facility. Hold on one second. Oh, my notes just got, Dad, I'm so sorry. Hold on. Did I lose you guys? My screen just totally went blank.
We still see and hear you.
Okay. Take just a moment here. Okay. Well, I'm going to have to, I should be able to go off of my memory at this point, but my apologies. My access to this internet document I was reading there we go, glitched. Okay, so my apologies. So his career in nuclear industry as an operations manager for the largest nuclear reactor facility at the Hanford site in Tri-Cities in Washington. President of the United Nuclear Company division that produced the nuclear reactors for naval ships, and he was a partner and owner of a private company that manufactured precision parts for nuclear reactors and aircraft engines. He also has an extensive public speaking background on the risks and benefits of nuclear power and is a frequent presenter for OLLI at Montana State University and OLLI at the University of Arizona, which is in Tucson. So we are very honored to have you join us, Jerry, and looking forward to your presentation. Thank you very much.
Okay, thank you. How do I get the polls information off of my screen? Or maybe it's on everybody's screen.
You should just be able to click on it and it should
Yep.
Okay.
It's gone.
Also at the top it says live transcription has been enabled.
Just
I
click
can close
okay.
that. Okay, so we're off and running. Good morning. It's a real pleasure to be here, have an opportunity to address 6 OLLI groups. It's a real opportunity. I've given lots of OLLI talks at both University of Arizona and Montana State University. I've actually given lots of talks on the status of nuclear power over some years. And it's an interesting transition. If I go back and I look at 2 years ago when I was giving these talks, I would have concluded that nuclear power is probably not going to succeed in democratic societies. There were real safety concerns with Chernobyl, 3 Mile Island, Fukushima, nuclear waste. Capital costs for building plants was unpredictable and extremely high, which made the costs high. And the alternatives, solar, wind, and so forth, were markedly lower costs. So I think I was pretty pessimistic about nuclear power. Today is today. It's a different situation, and it's largely different for 2 reasons. One is the Russia-Ukraine situation, which has just changed the thing for 2 reasons. One is it's changed the whole energy balance with the oil and gas sort of circumstances. And then secondly, as you'll see later in my presentation, Russia is probably the leading country in the world in nuclear technology, and certainly will have the most operating nuclear reactors and has the most versatile nuclear reactor systems. And they're a major supplier of nuclear reactors to the world. I'm not sure how that's going to work out. So things have changed quite a bit. Now, I'm going to go into the presentation here, and I'm going to, when I said a year and a half ago, things were different. This is an article from the Wall Street Journal, March 4th, 2021, said nuclear power prospects cool after Fukushima. And that was certainly the case. 2021, nuclear power was on a decline. I just saw this article in the Wall Street Journal 2 days ago, the global nuclear comeback. And I'll read just the first paragraph here. Senator Dianne Feinstein, a long-term nuclear energy critic, which is certainly true, said in June she changed her mind about California's last nuclear plant at Diablo Canyon, closing what she said made little sense under the circumstances. That's a dramatic change for her, and it's a dramatic change in philosophy for the nuclear industry. And here's what the Diablo Canyon plant looks like. And you'll notice at the bottom it says this is due to be shut down in 2024. Still maybe an issue as to whether it'll be shut down. But it looks very much like the Japanese Fukushima plant, which is on the coast and got hit with a tidal wave. And so the world has changed dramatically in terms of its view of nuclear energy. Now let's talk about where nuclear plants are. You have 6 states involved in this. 4 of you don't have nuclear reactors. 2 states, Minnesota and Iowa, I think each have maybe 2 nuclear plants. Iowa, I think, is shutting one down. There's in the process of shutting one down. But 4 of the 6 states, you sort of aren't really involved at all with nuclear plants. And you'll learn that's kind of significant because the real issue with nuclear plants is we don't mind nuclear plants as long as they're not in our state. So for not in my backyard kind of a syndrome. This is an interesting slide that shows power production by source. And it starts off in the US here. And it shows that coal in the last 20 years has dropped about in half in terms of the amount of power it provides. Petroleum or natural gas is increasing in terms of the amount that it provides. Nuclear has stayed about the same. It's dropped off from maybe 20% down to 15%. But you'll see some really growing trends here in the yellow, solar, and the wind. Now, what's more interesting is to look state by state. And you'll see in the states that you're in, North Dakota, Montana, South Dakota, Wyoming, particularly Wyoming, tremendous coal. It ranges from West Virginia, which is almost totally coal. And you can see why the senator from West Virginia that has been sort of, if you're a Democratic, problematic in terms of his views of this, of the environment and so forth and so on. He represents a state that is 95% coal in terms of power generation. You can see the other states, California, Utah, Arizona, you'll see a rapidly growing trend in the yellow, which is solar. And we'll talk more about that. So we're going to start by saying, what happened to nuclear energy? 1953, the Nautilus submarine was launched. It was a technical marvel. It was a submarine that was completely powered by a nuclear reactor. 1 year later, the first nuclear generating station was built, used a spare aircraft carrier reactor, and operated flawlessly for years. Chairman of the AEC, the Atomic Energy Commission at the time, said that he was sure electricity would soon be too cheap to measure. You wouldn't have to measure it. And in fact, for about 30 years, there were hundreds of nuclear power reactors built all over the world. But today, for reasons we'll talk about, it's either the beginning of the end or maybe a slight new horizon is beginning. Nuclear power, you have to remember, was born with a big bang. The only reason we have nuclear power is we needed to produce nuclear bombs to use during the Second World War. So today we're going to talk about that. We're going to talk about how we got the first big bang. We're going to talk about how a reactor operates. Are they safe? Are they economical? And we'll close by talking about some new technologies: fusion, thorium, molten salt reactors, small nuclear reactors. But you have to remember, nuclear power started with a big bang. And somebody told me one time that if the first use of gasoline had been for napalm bombs, we probably wouldn't be using as much oil as we use today, because people would remember that. And that's certainly the case when people think about nuclear power and they think about a nuclear power plant. They think it's a bomb that's getting ready to go off. Well, that's true. The only reason we started building nuclear reactors is we're required to make World War II atomic bombs. Now, there's only two ways you can make an atomic bomb. You can use uranium-235 or plutonium-239. Those are the two elements that you can bombard with neutrons and create a nuclear explosion. Now, uranium-235, you need 90% uranium-235 to make a nuclear bomb. Unfortunately, natural uranium that we mine is 99.3% uranium-238, 0.7% uranium-235. And you just can't separate those elements. Chemically, they're the same element. So the way you do that is you centrifuge or gaseous diffusion, and you separate them by weight. Uranium-235 is a little lighter than uranium-238. And that produces what we call 90% bomb grade uranium-235. And some of you remember the Oak Ridge Project. That was the World War II Manhattan Project, where they had a lot of centrifuges, gaseous diffusion plants to produce the uranium-235 that were needed. Some countries, Iran is one that you recognize, they keep talking about the number of centrifuges they have because they're concentrating natural uranium to create concentrated uranium-235. So that's one route to making a nuclear bomb. The other route, which we're going to talk a lot about, is plutonium. Plutonium does not occur in nature. You have to produce plutonium from putting uranium in a nuclear reactor and bombarding it with neutrons, and it creates plutonium. And the Hanford Project, World War II Manhattan Project, there were 8 nuclear reactors ultimately built to produce plutonium for use in making nuclear weapons. So the whole basis for starting nuclear reactors was to make nuclear weapons. And here's the two types of nuclear weapons. One is called a uranium gun design. These are the two that were used in the Second World War. It uses 141 pounds of uranium, and it makes a 15 kiloton explosion. That's the kind that we used in the Second World War. The second one is a plutonium bomb. That was a little more tricky to design. The uranium bomb, you just had a lot of uranium here. You fired a uranium bullet into it. It created a chain reaction that caused a nuclear explosion. This one was a little trickier. You took plutonium in a sphere and you built explosive lenses around it to compress it when they exploded to make it a nuclear weapon. And this is the one that they were a little worried about whether it might work. And that's the one they used in the Trinity explosion in New Mexico to test the concept before they used them in Japan. But you'll notice that the uranium bomb takes 141 pounds of uranium, plutonium takes 14 pounds. So the goal here was to make a lot of plutonium to create nuclear weapons. Now, how do you do that? Well, we have what's called a chain reaction, where you bombard uranium with neutrons, and it splits into other components and gives off 2 more neutrons, splits again, gives off 2 more neutrons. So you wind up with a chain reaction, and you can either have a controlled chain reaction, which would be a nuclear reactor, or you can have an uncontrolled one, which would be an atomic bomb. This is the first nuclear reactor that was built under the University of Chicago campus in a squash court area. And it was built by Enrico Fermi, and it went operational in 1942. This is a drawing that was made. They didn't want to take pictures because they weren't quite sure what would happen. And this shows the nuclear reactor. The nuclear reactor is a pile of graphite cubes that are drilled in the center, and they're filled with uranium that you can control the chain reaction by pulling the control rod out. And this is Enrico Fermi, and he's pulling the control rod out to create a chain reaction here that will convert the uranium there into plutonium. Now, there's another term that's associated with this, because they were worried that if it got a little bit out of control, how would you shut it down? It's sort of hidden by my picture here, but let me get rid of that. That shows some people up here on top of the reactor, and they have a rod there, a safety rod, that they're going to drop into the reactor if it starts getting too reactive, and that will absorb neutrons. It's a boron rod that absorbs neutrons, and it'll shut the reactor down immediately. And this was called technique at the time was called scramming the reactor. Now, that means safety control rod axeman, because the way this worked is you had the control rod with a rope on it, and you had a fellow up there with an axe. And if it got too reactive, he was given a signal, and he hit the rope with the axe, break the rope, and it would drop into the reactor. So that term is still used frequently associated with nuclear reactors. You'll hear that periodically, that it's unfortunately that the reactor scrammed. Well, what that means is that the vertical safety rods dropped in and shut the reactor down. So it's called safety control rod axeman. Now, this created a design for the B reactor complex at Hanford, Washington, which was built in 1945. 44 and 45. And the whole purpose of this is to create plutonium from uranium. And this has 3,000 tubes of graphite that are drilled out. There are aluminum tubes that are placed through the graphite. There are uranium pieces called slugs that are placed through the aluminum tubes. And you run water from the Columbia River, which is out here, through here to cool it. And then the water is discharged back to the Columbia River, and that cools it and allows it to operate and slowly convert the uranium-238 to plutonium. This was called B reactor. It was the first reactor built. There were ultimately 9 reactors built at Hanford that were used to produce plutonium. Now, this is a control rod of B reactor, and that's yours truly sitting there. I had a little more hair at the time, that you can see there. That's a museum now. And it's a marvelous museum at Hanford, Washington, or Richland, Pasco, Kennewick. And I'd certainly encourage any of you that are over in that area, if you have an opportunity, to go tour that museum. It's the first operating nuclear reactor that was made to control making plutonium from uranium. And it's a marvelous tour. Now, let's talk about the number of nuclear reactors today. Today, there are roughly 450 nuclear power reactors. Now, what's a nuclear power reactor? Well, that's a reactor that you have graphite pile or aluminum tubes. They're filled with uranium. You run water past the aluminum tubes to cool it, and you heat it up, and it creates energy by creating hot water that either directly or indirectly boils. And there's 450 power reactors in the United States, 225 research reactors, 175 naval reactors, 4 icebreaker reactors that are on Russian ships. And in the past, 35 space reactors were made. We only made 1 in the United States. The Russians made 34. And the concept was to be able to shoot a missile up into the air, put it in orbit, and have a nuclear reactor that could continuously operate and power it. I'll show you the picture of the one that we did. Currently, people will ask, well, do we have a lot of nuclear reactors up here today powering satellites and so forth? No, we don't. They're not nuclear reactors. They're actually what powers satellites today would be a suitcase size system that's filled with uranium-238, and it's a battery. It generally generates electricity the same way a battery does. So it's not an operating nuclear reactor. This is what the operating nuclear reactor looked like when we launched it in 1965. It's called a SNAP reactor. It ran for about, I think, 10 months, and then it had a problem with the heat exchanger and was shut down. And ultimately, I think it came into the Earth's atmosphere and disintegrated into small pieces. But that's the first space reactor that we made was in 1965. Well, this is a ship. This is a picture of the Navy ships, aircraft carrier, destroyer, and a frigate. Doesn't show a submarine because they're underwater, but the Navy is really the basis behind the development of the whole nuclear energy program in the world. And this is E equals mc squared. E is energy, M is mass, and C is the speed of light squared, which is a very big number. So the concept that Albert Einstein came up with is if you can take a very small amount of mass and bombard it with neutrons, cause it to split, and you weigh the amount of material before and after it splits, a very small amount, 0.7% or so, will go away and be multiplied by the speed of light squared and create a tremendous amount of energy. So I thought this was a really interesting picture for 2 or 3 reasons. One is it shows the formula. Secondly, it shows the Navy system, which again is really the basis of the whole nuclear reactor system today. Normal nuclear powered ships. The United States has got 72, Russia's 38, and you can see the rest of them. Aircraft carriers, we have 11, France has 1. France, as you can see, is clearly the leader in terms of nuclear development for nuclear powered ships, and also nuclear development for nuclear reactors for power. Now, the difference between a commercial and a naval reactor, and this is something that you sort of need to understand, commercial reactor would be 1,000 megawatts in size. Now, what's that mean? That's 1,000,000 megawatts. That's about 20% or 30% of a major Grand Coulee Dam kind of a complex that generates electricity. Naval reactors are much, much smaller. They're 50 to 100 megawatts in size. Commercial reactors have to have some uranium-235. Remember, the only fissionable uranium is uranium-235, and only 0.7% of that is naturally occurring. So you have to concentrate it to get to 5%. Navy reactors use 95% uranium-235, which is really bomb-grade material. You can take that material, put it in a different format, and make a nuclear weapon out of it. So in summary, a nuclear reactor uses 30 tons of fuel because it doesn't have much uranium-235. Navy reactor uses 800 pounds of fuel. The difference is you refuel a commercial reactor every year. Basically, 1/3 of the fuel has to be taken out, and you process it as waste. Nuclear reactors in submarines or aircraft carriers or destroyers, they last 15 to 25 years. They're highly they have a high amount of energy because of the high amount of uranium-235, and they use what's called a burnable poison there that will slowly absorb neutrons, and maintain a constant power level. And with a naval reactor, you replace the entire reactor, and usually you replace it once, or maybe not even once, during the life of a ship. Commercial reactor covers a city block. Naval reactor is about the size of a large SUV. Now, how does a power reactor work? Well, this is a slide that shows a coal-fired electrical generating station. And if you understand this, you'll understand a nuclear reactor. Coal-fired station basically is a boiler. And you put coal into the boiler and you heat it up. You boil it. And it boils water. Water then goes over, turns into steam, and drives a steam generator, turbine, which creates electricity. And then the water is condensed, comes back down, and is recirculated. So the whole heat process is created in this system here by burning coal. Now, we're just going to change coal to oil, to gas, or to nuclear, and it's all the same process. Now, how's uranium made into fuel? Well, as I mentioned earlier, uranium is a naturally occurring element. You have to enrich the uranium to 235. You form it into little pellets. You put the pellets into a fuel rod, put the fuel rod into a fuel assembly, put the fuel assembly into a nuclear reactor core, and you wind up with a core of thousands of fuel elements, and you have control rods that you move up and down that control the power level that the reactor operates at. And it's a big it's a big system. Pressurized water reactor. This is what 80% of the reactors in the world are pressurized water reactors. And they generate from 1,000 to 1,400 megawatts. And they operate by having a reactor vessel. You've got the uranium in the tubes here. And you have the control rods that move up and down. Heats up the water goes through a steam generator. Steam is generated here, goes over and runs a turbine, which runs an electrical generator, and it's condensed and comes back into the reactor, and you'll see these big cooling towers at all of the nuclear plants. Now, this is a pressurized water reactor. 80% of the reactors in the world are pressurized water reactors. They also have boiling water reactors, which they use directly by boiling the water from the reactor, and it comes over and it runs a turbine itself. So they eliminate the secondary loop. It's called a boiling reactor design. It's a General Electric design, and 10% or so of the reactors in the world today are boiling water reactors. So a 1,000 megawatt reactor has 50,000 fuel rods, 18 million uranium pellets, 30 tons of uranium. And every year, 1/3 has to be removed to provide new reactivity. And it'll power roughly 750,000 homes. Percentage of nuclear generation in the world. Well, France, about 80% of their power is provided by nuclear power. And you can see it goes on down to where when we get to the United States, we're down around about 20%. And you can see that the European countries generally have a much higher percentage of their electrical power is generated by nuclear energy. Number of nuclear plants in operation, while we dwarf the rest of the world in that. We have 96, 97, 98 nuclear plants running. France is next with 58. China, Japan, Russia, and then you can see them working their way on down. So there's a number of nuclear plants that we have that's almost twice as much as the rest of the countries. But planned nuclear reactors is a different kind of a situation. As a result of all the issues that have occurred, the only countries that are now planning on building a lot of reactors are China, India, and Russia. You can see we're down with 2 reactors, I think, down here at the bottom. It's hard to see, but we have 2 that we're building. and we actually only have one that we're building. So any new reactor construction today is in what I would call non-democratic societies, China, India, and Russia. World energy supply by source. Well, still today, roughly coal is about 40%, 35 or 40% of the energy is generated by coal. Gas is around 20%. Hydropower is kind of a constant, 15%. Nuclear, you can see, has been on a declining scale for the last 20 years. And now we're down around 10% of the power being provided by nuclear power. The really growing ones are wind and solar, and maybe other renewables, but it's a dramatic increase in the wind and solar. How dramatic? Well, this is a complicated slide you don't need to understand, but basically it will tell you that today, 21% of the power in the United States is provided by renewables, 19% by nuclear, and 37% by natural gas. They're predicting that in 2050, 44% will be renewables, and nuclear will drop off even more, and coal will go from 23% to 10%. This one shows a projection of the renewables, shows solar going from, maybe 19 or 20% today up to 50%, shows wind increasing quite a bit, shows everything else is kind of constant. Now, this may be optimistic, but even if it's optimistic, it shows you that in the next 20 years, solar and wind are going to be the dominant places where we'll gain in generation of electricity capacity. Now, cost. This all boils down to cost. Somebody said one time about politics even, Biden's suffering that problem. It's the economy, stupid. If the economy is doing well, we re-elect people. If it's not doing well, we vote people out and vote people in who probably won't do any better job, but it's the economy. And that's certainly the economy in terms of cost. Now, this slide's interesting in that it shows the cost of generating electrical power for a 12 or 15-year period. Now, it's called levelized cost, which means it considers the capital cost along with the operating cost. And you can see the only one that's increased dramatically is nuclear. And you can see how it's spiked up constantly, really spiked up in the Fukushima incident period there. And now it's increased 33% in roughly 11 years. Coal has remained about the same. The dramatic ones are solar and wind. Solar has dropped a factor of 10 in terms of its cost, and it's continuing to drop. So solar energy has become a very economical source of generating electrical power, and it will continue to do that and continue to dominate. Now, one thing you have to understand about reactors also, in a totally separate subject, is remember I said people think reactors blow up. Well, reactors don't blow up. They don't detonate. You're not sitting there with a nuclear reactor that's going to turn into a nuclear bomb. What happens with a nuclear reactor that can create a problem is a reactor scrams. Remember Safety Control Rod Axeman? That guy's up there with a hatchet getting ready to break a rope. Safety rods or balls drop and the reactor shuts down immediately. Old style graphite reactors like the Hanford reactors and Chernobyl reactors, and Chernobyl is an example of that. You can get fuel elements that rupture, overheat, and they have graphite tubes that burn, and there can be a significant safety problem with them. That's why Chernobyl was such a problem. We had one reactor like that at Hanford that was very much like the Chernobyl reactor that we quietly shut down after the Chernobyl incident. Modern reactors, like the 3 Mile Island reactor that had a problem, or Fukushima reactor, they're a little different. It takes days or weeks for radioactive fuel to cool, and that's a problem with a reactor. You lose coolant flow, the exposed fuel melts and vaporizes. That's the risk you have today with a modern reactor. Even fuel that you discharge once you shut the reactor down is so radioactive, it has to remain underwater for 2 to 5 years to be constantly cooled. Well, how does that happen? Well, you have a reactor that's operating at full power. That's 1,000 megawatts. And it shuts down. And it immediately shuts down. And after it shuts down, it's still so radioactive, giving off heat, that it operates at 7% of its original power level for an hour or two. Now, 7% of a 1,000 megawatt reactor is larger than a naval reactor. So when a regular power reactor shuts down, the heat being generated, even after it's shut down for a period of time, is more than is generated by a reactor that runs a submarine. So the decay heat slowly decreases over weeks. And as I said, you have to keep the fuel underwater for 2 years or so, and then you continually have to cool it after that. The type of material that's in the waste from a nuclear reactor or in the spent fuel has what's called a half-life, which means that in 58 years, the neptunium-239 that's there will be 1/2 as active as it was. Xenon-133 is a very short-lived. Means 5 days reactivity to xenon. Half the xenon is gone. 5 days later, half is gone. Well, when you get down here to cerium, it's about a year. You get down here to the plutonium, cesium, and plutonium, you wind up with years half-life, in some cases, hundreds of years of half-life. So you have a long time period where you have to cool radioactive waste. The nuclear energy group puts out a slide here that I found that says nuclear power does not produce any significant wastes which are dispersed to the environment. Instead, they're retained within the plant and managed for the long term. That's true, but that doesn't mean anything. It just says that the radioactive material has to be kept on the site. In real life, nuclear waste is really the Achilles heel of the nuclear industry. You get 10 tons of waste each year from a reactor that you have to do something with. 5% of that is highly radioactive. It includes plutonium-239, which when you separate that out, you can make a nuclear weapon from, and it has a 24,000 year half-life, which means every 24,000 years, it's half as radioactive. Now, that shouldn't really be a problem because the solution to the problem is you simply chemically separate out the 5% of the hot waste and encapsulate it and bury it someplace. And that's what back in the 70s we had planned to do. We're going to build a plant to separate out the 5% highly radioactive waste. We're going to encapsulate it and we're going to bury it in Nevada. That was the case. But President Carter in 1976 decided that building a reprocessing plant, you would create plutonium because you have 1% plutonium in the waste. You create that and that can create bombs. So he did not want to have a system where you were generating material that could be bomb-risk plutonium. So he decided that we would not reprocess fuel. And we have not, since 1976, ever reactivated any kind of a fuel reprocessing system. So there's no way that we can, in the United States and even mostly worldwide, process spent fuel and concentrate the waste. Now, Nevada, Yucca Mountain, that was the other arm that was selected in 1982, where we're going to have an encapsulated waste burial site. You take the waste, you concentrate it, put it in a ceramic tube, and you bury it in Nevada. Unfortunately, 40 years and $15 billion later, Nevada decided they didn't want to do that. It wasn't in their backyard. Harry Reid was the senator from there. And so we don't have any place to bury waste. So there's a lady that's getting her PhD at Harvard, and she just did a paper on nuclear waste looking for a home. And this is a picture on her introduction to her presentation. And I thought it was kind of an interesting picture. It does show fundamentally that today we don't have any solution for nuclear waste. We basically have to store it underwater for 5 years, and then we build a dry cask storage system and we store it on site for 30 to 60 years. So every nuclear plant that exists today, and I showed you the ones, and you have some certainly in Minnesota, in Iowa, your nuclear waste there are going to be stored in dry cask storages on that site for 30 to 50 years. I think this is the time to take a break. And what I'd like to do is sort of take maybe a 2 or 3 minute break and then answer any questions that you may have. So let's do that.
Sounds good. We'll get started again at about 10:45, 43.
Sounds good. And somebody can keep track of the questions, and anybody that has questions, I'll answer before we get started.
Thea, would you like to facilitate the questions? I see there's some in the chat.
Yep, definitely.
What about cold fusion? There was excitement about that a while ago. How's that going?
The question is cold fusion. I think that's a lark. Fusion, I'm going to talk a little bit about fusion later on when I talk about processes, but the article I remember, I think it was in Utah actually, that they came up with a process they thought could generate electricity by cold fusion. And I haven't done any research on that since then, but I think that's I would class it in one of two categories. Either it was intentionally a program that was designed to create interest that didn't work, or there was information created during the process that was misinterpreted, that it generated some energy. But I don't think cold fusion is a viable alternative for creating electricity. But we'll talk about fusion later on.
Is there a credible source of information that compares the pros and cons of various energy sources, kind of soup to nuts, you know, all the way from building it to disposing of it, you know, because we talk about like windmills, for example, but the blades only last for a certain amount of time, and now there's a problem disposing of the blades because a lot of landfills won't take them. They're made of fiberglass or whatever. So is there any place where these comparisons have been made, the cost comparison, the waste disposal comparison?
There are. It's unfortunately, it's almost like politics. You know, you have the right wing on one side and the left wing on the other side, and that's the case when you start doing searches for energy costs. You're going to find a website that's got a lot of marvelous information in it that's put out by the American Nuclear Society. And it's going to conclude, as that slide I showed you, that it's really nifty with nuclear waste because you just store it on site and it never is released to the environment. So yes, there is. I think the one I found that works the best, it measures what's called the levelized cost of energy, LCOE. So if you go to a website and type in levelized cost of energy, It'll find different places for you and measure the cost of energy. And what that does is it tries to consider every part of generating energy. It covers the mining cost, it covers the capital cost of building the plant, covers the operating cost, it covers the cost to shut the plant down and restore it to its natural state. And they're fairly good at that. Now, there's a lot of uncertainty in those numbers because, you know, who knows what it's going to cost to get rid of the nuclear waste? Who knows what it's going to cost to get rid of the windmills? But I guess the answer is there are relatively honest assessments of what people think the cost might be. And I would start with that levelized cost of energy websites and use that. Doesn't mean they're right, and they probably aren't right, but it is hard finding information, and you'll find a lot of information that favors. If you leave out the cost of building a nuclear plant, nuclear is the most economical way to generate electricity, and you'll see that used frequently. Unfortunately, the cost of building a nuclear plant today is billions and billions of dollars, and you can't even define what that number is. So the long-winded answer to that is yes, but be careful how you use it.
Jerry, we do have a few questions in our chat that have come up. One of them from Julia: is fracking a concern vis-a-vis nuclear waste storage?
What was the question now?
Is fracking a concern, like in relation to nuclear waste storage?
I don't know the term fracking. I don't know how that.
That's being used a lot right now with tapping into oil, especially in like North Dakota. It's a term that they use for the type of drilling and access that they have.
So but what's the intent of the question? Is the intent of the question is if you bury nuclear waste, is the process of the earth structure over a period of time going to cause issues with the nuclear waste?
Julia, do you want to address that question?
Yeah, excuse me. Thank you. I'm just concerned about fracking in general because they're digging and pounding and disrupting the structure underground in order to, and they use a lot of sand in order to gather low grade oil, and then they use that oil. But there's a concern, I think, about earthquakes, and I'm just wondering, when people are, it seems to me, doing a lot of fracking with this oil exploration, do they have to go through some kind of process so they don't do it near a nuclear waste site? You know?
Yeah, I don't think there's a relationship there that fits. First of all, there's not all nuclear waste sites are located at nuclear plants. Now, there's a lot of nuclear waste that has been generated as a result of building the nuclear reactors in Hanford, separating all of your plutonium from the uranium. I mean, that happened 80 years ago, and we still have tanks there that have that nuclear waste in it. So I think if you're going to do any fracking or anything in Hanford, Washington, around that area, you may have some risk with that. But if you're fracking in the middle of South Dakota or North Dakota, it's not going to, I think, have any effect on the nuclear part of it.
We do have a couple other questions. Could nuclear waste be put into space, or the question is flung toward the sun and get rid of it that way?
Well, there are certainly issues. There are certainly people that say what we should do with it is put it in containers and drop in the ocean, or put it in a spaceship and fire it towards the sun, and hopefully when it hits the sun, it'll disintegrate. The ocean is not practical for a lot of different reasons, and putting it in spaceships. You're talking 10 tons of waste every year from a nuclear plant, and you've got, you know, hundreds of nuclear plants. So I don't think that's a feasible issue to put it into space either.
Another question from Karen: if the US has so many nuclear power plants, why do we produce so little nuclear energy comparatively?
It's just a matter of the generation. Nuclear plant generates 1,000 megawatts of electricity. That's the equivalent of maybe 25% of a major hydroelectric plant. We haven't built a nuclear plant in the United States in 20 years. Our nuclear plants here have an average life of 45 or 50 years. So we don't have any new nuclear plants. So that's why you see the generation of nuclear power going from roughly 20% down to 10% as energy increases, the use of energy increases and whatnot. Nuclear doesn't, so its usage slowly drops off. And you can't take a nuclear plant that you built that's sized for 1,000 megawatts and suddenly run it at 5,000 megawatts. You can work hard and maybe get the approvals to go up to 1,200 megawatts, but it's not something you can just pour more uranium in and run at a higher level.
Okay, one more question in the chat and then we'll get to you, Marcy. Barb asks, does France recycle nuclear waste safely? I read that they accept it from most of Europe.
They were going to have a process of processing nuclear waste. I'm not exactly sure where that's at right now. After the Fukushima incident, France decided they were going to slowly shut all their nuclear reactors down and go out of the nuclear business. That's changed somewhat as a result of the Russian situation and so forth. But I think right now they do not have a process of processing nuclear waste. The country that has the process for processing nuclear waste would be Sweden. And if you look at Sweden or Switzerland in terms of processing nuclear waste, they have a system that they're going to use. And it's basically taking the nuclear waste, storing it for 4 or 5 years underwater till it cools down. And then once it cools down, they're going to put it in some kind of a container, encapsulated container, and they're going to bury it on a site they consider safe, or they're going to find a site like we were going to find in Nevada. And they're pretty far along with that. The basic concept in Sweden is that they're going to have nuclear reactors, but no nuclear waste material is ever going to leave the country. They're going to store it. So the answer is they're probably the furthest along in terms of coming up with a way to store nuclear waste, but they're just going to bury it, keep it.
Okay, Marcy, go ahead with your question.
Isn't one of the nuclear plants in California built on an earthquake fault?
Sure, Diablo Canyon is the one that they were going to shut down in 2 years. Dianne Feinstein now said, well, maybe we're not going to shut that down. So yes, a number of nuclear reactors are built. Well, most nuclear reactors are built on coastlines because they need water to cool it. And I'm going to talk about the Fukushima incident, so that'll make a little more sense. But yes, there are a number of nuclear reactors that are built on fault lines, and a lot of them are being shut down.
Interesting. Just before we get back to your talk, Bobby put a few things in the chat that I think that everybody should take a look at. There's a link that talks about those cost comparisons, those comparisons of power, and she has some other great information there too. Gerald, I think we're through all our questions for right now, so let's continue.
Okay, here we go. We ready? Let's talk about safety. Everybody and I talked about nuclear plants or nuclear bombs, the plant melts and all that kind of stuff. So let's talk about statistically, how safe is nuclear power? Well, nuclear power is 10 times safer than any other thing that's used to generate power. This slide here will show you that, and this is measured in deaths per year for trillion watts or some such thing, but it's a comparative. Coal is the most dangerous. The world average on coal is 161 deaths per whatever the unit is. China is much, much higher than that. US is much safer in terms of their coal. Oil is at 36, comes down to solar rooftop is pretty safe. This must be from people falling off roofs when they're doing it, but I don't quite know how. Wind is a little more safer. Hydro is pretty safe, other than one event in China that occurred. And you see nuclear is off the bottom of the scale in terms of safety. So there is no question that nuclear power is by a factor of 10 the safest way to generate electricity. And nobody disputes that. I mean, it's, I think, just, but you have to put that in concept. And the concept I give you is that airplanes, flying on commercial airlines is clearly the safest way to travel. But what happens when two commercial airliners crash? Everybody says, well, that's it, man. Hang on one second.
I love these these home office Zoom background
This is the
noise.
real world, right?
Right? Coffee grinding, dogs barking.
Exactly.
Okay, I apologize for that. We have an Australian Shepherd that gets paid a lot of money to watch the house, and he got carried away. So I was saying that there's no question nuclear power is the safest thing, but the comparison I was making was everybody should fly commercial, but when two planes crash, everybody says, yeah, I'm going to drive because it's a lot safer. Well, driving your car is, 20 times more dangerous than flying a plane, but it doesn't, you don't believe that when you read about the plane crashes, and that's the same with nuclear. Well, let's talk about some of the major nuclear events that happened that shaped the world. First was a movie. The China Syndrome movie was made in 1979. Starred Jane Fonda and Jack Lemmon. Reactor core melted and it started headed to China. That's why it's called the China Syndrome. That's what happens when a nuclear fuel in a reactor melts. It gets so hot, it goes through the container, starts going into the earth. And it was an Academy Award winning movie. Unfortunately for nuclear, 12 days later, we had the 3 Mile Island incident, which was a nuclear reactor in Pennsylvania, where what actually happened is a valve stuck open and they started to lose some water level in the reactor. And there was a faulty light that was involved, and there was an operator error. He didn't really believe that they were losing water that much. And as a result, they had a partial meltdown of the reactor fuel. And that's a big deal. You got the reactor fuel that's melting. There was no radioactive release at the boundary of the site that exceeded the safety standard. So it was a dramatic incident. First time a commercial reactor had melted and the fuel had melted. And that created quite a bit of a problem in the nuclear industry. And the next one was Chernobyl. Now, Chernobyl is a different kind of a system. Chernobyl is an old style Hanford type graphite reactor. You remember the B reactor I showed you at the start of the presentation when I had my picture in the control room. They lost flow to some of the tubes. The fuel in the tube melted and graphite caught fire. And it was a real turmoil. It still is. It created 50 deaths immediately. You can estimate anywhere 4,000 deaths later. There's been lots of specials that have been run on the Chernobyl situation, and it was a real mess, and it created some real problems for the nuclear industry. But the Fukushima incident that occurred March 11th, 2011 was the crowning blow. And it was a magnitude 9 earthquake, created a 50% tsunami wave, The earthquake ruptured some of the coolant piping, so the water flow to the reactor was stopped. The tidal wave disabled the last ditch cooling system, and they wound up at the end having to cool the whole system with fire trucks that they pumped water from the ocean into the nuclear site. So it was a real disaster. At a 100-year incident or 200-year incident in a plant that was designed to withstand a 99-year incident. So it was a real problem. The biggest design error they had was the location of their last ditch cooling system. Their last ditch cooling system that's supposed to come on and save the reactor from melting, that was located on the sea side of the reactor or on the water side of the reactor instead of the other side. So it was subject to the tsunami wave that hit it, and it hit it and it knocked it out. And that was just a design error that probably nobody thought of at the time, because you're thinking again in terms of 100-year events. Basically, it overwhelmed the 100-year design accident criteria for a nuclear reactor. The nuclear fuel in 3 of the 5 reactors melted. There was massive spreading of the radioactive material in the area. 18,000 people died. Maybe 50 to 100 were nuclear related. The others were related to other types of things. There were 160,000 people forced from their homes, but more people died in moving incidents than they died in a nuclear reactor incident. So if you look at the statistical data, this is a horrible, horrible situation. But if you look at it in context of the world's history of nuclear power and whatnot, that's not particularly significant. Well, what happened? This is the nuclear reactor, and there are the core of the reactors here. Control rods move up and down and control the radioactivity in the reactor. And you've got pumps that pump cooling water through there, and the steam generators. Steam generator comes out, runs a turbine, is circulated back in. So the earthquake was severe enough where it ruptured some of these lines, and the water escaped and blew up into steam from the reactor. And you have a last ditch coolant system that exists, that water is pumped in from the last ditch effort. And you usually have 3 systems. You have the primary system that you use. You've got a backup system, which are emergency generators that run off of electricity that will run coolant pumps. And the third one is you always have diesels that are fueled with diesel fuel that come on and pump water from a third source to the reactor to cool the core. Well, that third source was located on the water side of the reactor, and it was hit by the tidal wave and wiped out. So 3 of the cores here basically melted. They're still melted. And it's still a significant problem. They're not going to have access to this to be able to do anything for 50 years. The area around here is highly contaminated, so it's a significant issue. The Fukushima incident was really basically the end of the modern nuclear era. Everybody said, well, Chernobyl, a big deal, they're Russians, and they shouldn't have been running that reactor anyway. We don't have any of those, and we're not going to have that kind of an incident. And so Chernobyl, everybody said, that's okay. 3 Mile Island, well, the emergency system worked, so it worked pretty well. Fukushima was a modern reactor. Japanese are considered the masters of technology. 100-year disaster did occur, and a lot of sites like that are vulnerable. And this is sort of like the US space system. Remember when the Challenger blew up in space and we wind up watching 7 people killed in space, including a teacher? If you're familiar with the space program, you'll know that ended our space program, basically. The government decided that they're not going to have any more blow-ups in space of spaceships that they're responsible for. And that's why we started paying the Russians to take us to this, to the space station. That's why Musk, they don't mind Musk taking a risk with his system. They don't mind the Amazon guy taking a risk with his system because it's not, doesn't expose the politics and doesn't expose a political individual, and it doesn't expose people to the cost that's borne by the people doing the program. No political leader really wants a nuclear event in his country or state, or do they want to underwrite the risk of a nuclear event occurring financially, like the Fukushima incident. Now, I want to talk a bit about Admiral Rickover. People don't realize he is the father of the nuclear industry, both commercial and Navy. Nautilus submarine was launched in 1953. Shippingport Nuclear Station, 1955, is first to generate electricity. When the Nautilus was launched in 1954, it was the first use of nuclear reactors to do something, quote, useful. It ran a submarine. The next thing they did, and Rickover did it, is he built a nuclear plant that could generate electricity. And his designs have maintained use for 80 years. The Rickover come up with the concepts of nuclear reactors use zirconium for cladding for the fuel. They use zirconium tubes to put the fuel in. All of that is based on Rickover designs. Rickover's pressurized water reactor design dominated the industry for 60 years. Unrivaled safety record. He had an unrivaled political and public support. And he built reactors from 50 megawatts to 1,000 megawatts. Even today, 80% of all our reactors are run on Rickover design reactors. Well, are there problems with that PWR technology? Sure, one is it's high pressure. You have to have enough pressure to generate steam to generate electricity. Well, that means if you get depressurization because of the vessel failing or leaks, you lose your coolant to cool the reactor. You need highly enriched uranium-235 for power. A byproduct of the spent fuel is plutonium. You have to refuel every year. Plants are now huge. They're 1,000 megawatts. They're big, they're unpredictable, they're redundant, they're overly complicated. And today they're probably over safe, even though you had the Fukushima incident. This is a submarine engine control room. This is a control room for running a submarine with its nuclear reactors. Rickover's design, Rickover carefully controlled that, and it's still carefully controlled. This is a commercial reactor control room. And one of the reasons for the 3 Mile accident they had is that their control room was too complicated. They had an annunciator someplace that went off that nobody noticed. And that's what's happened with the nuclear industry, is it's gotten so large and so expensive that it's even hard to manage. You can see all of these alarms and controls in here. And this is sort of like flying an airplane. You know, what's a pilot do when he flies an airplane? He flies an airplane from New York to Los Angeles and does nothing. He sits there. And that's the way a nuclear plant is. So it's an interesting psychology to build a nuclear plant. Now let's talk about the future. We have the National Reactor Testing Station in Idaho, which for years is where they built reactors to test different concepts. Different reactor designs just haven't caught on. And it's not that they haven't been tried. National Reactor Testing Station in Idaho Falls, there are 51 different nuclear reactor designs tested. Very low interest in that now. There's only 3 reactors that are being tested there. All shapes, sizes, and possible uses of reactors were tested between the 60s and the 90s. They tried to design reactors to put in aircrafts, using ships. Russia's got 4 icebreakers they use nuclear reactors in. They're going to run railroads with nuclear reactors. They're going to run trucks with nuclear reactors. They're going to run spaceships with nuclear reactors. They're going to have nuclear reactors you can carry in a suitcase to go provide energy for things. None of those were they able to come up with a design that was workable. They tried thorium because it was going to eliminate plutonium. They used heavy water reactor because you can use U-238s to the U-235. You have breeder reactors that create their own fuel. High temperature gas cool reactors, they operate at a much higher temperature and you can generate a lot more electricity. Fast flux reactors use more neutrons, are more efficient. So this is not a case of technology that hasn't been explored, and it's been explored and hasn't been found to have any practical use. Molten salt reactors, that's popular today. It's a low pressure. You use molten salt for the coolant instead of water. So if you take sodium and use sodium for the coolant, it can operate at a much higher temperature in the secondary loop and create a much more efficient reactor. A couple of problems is that sodium freezes at room temperature and it explodes when it gets hydrogen or water contact. So the Navy twice tried to use molten salt reactors and gave up both times. What's popular today are two types of reactors: the natrium reactor that Bill Gates is developing, and the other type of reactor that's just called a small nuclear reactor. But let's talk first about investments in technology. This is a curve that shows how much money is spent in funding different methods of creating energy. And you can see nuclear is down here, sort of at the bottom. Wind, there's been billions of dollars spent. Solar, billions of dollars spent. And other renewables, but not much in nuclear. That's sort of changing. Today, the government has decided they're going to spend $2 billion to match Bill Gates' $2 billion to build a liquid salt plant that's going to operate in Wyoming in the coal fields, where they'll be happy to have it because there's so much unemployment. So how's a molten salt reactor work? This is the kind they're thinking about putting in Idaho Falls in Wyoming. Well, it's complicated. You wind up with a reactor that's got fuel that you operate at a high enough temperature so you can recirculate it. And it's got a nifty kind of design. It's got a freeze plug here that has the fuel in it. And if it overheats, this freeze plug melts and all the fuel drops down into canisters where they've got material that absorb neutrons and will shut it down. So it's a nifty kind of a system. And it's got a heat exchanger, a couple of heat exchangers, and it's using, again, molten salt. Well, you've seen what a PWR, a pressurized water reactor, looks like, and it's a lot simpler than this. And the real issue on this is going to be cost and maybe reliability. Small nuclear reactors are popular now. The idea, you take a reactor like the Navy has, it's small, and you set it up someplace, and you could hook lines up to it that take the hot water and run a steam generator. And maybe if you build a lot of these, and they're all small, they're 50 megawatts in size, they'll be low cost, and you can use them. And this is the concept that they're going to have, supposedly being built in Idaho Falls. Montana has supported this concept. They said that they will take energy that's generated by the small nuclear reactors in Idaho Falls and use it in Montana. But I have a feeling if they showed up in Bozeman and said, you know, hey, we really thought about this, so we don't want to put it in Idaho Falls, we'd like to put it in Bozeman, you'd have a little bit different of a situation. Well, let's talk about fusion. This is Dummy's Guide to Fusion. Well, fusion is basically the process in the sun that creates energy. E equals mc squared. E is energy, m is mass. If you weigh all the hydrogen, combine it to helium, you lose 0.7% to energy, and you multiply that by the speed of light, you get lots of energy. So fusion is a process of the sun compressing hydrogen into helium. There's two concepts underway now. One is in France. It uses supposedly magnetic waves to contain the fusion. And they've had some progress there. By progress, recently they were able to generate more power than it took to run the place for a few milliseconds. So they're having some progress. The other process is a national ignition facility in Livermore Labs. They're using lasers to control and contain fusion. And they've had some recent progress. So fusion, I think, may have a future. I used to say that fusion has always been a 50-year future moving target. Maybe today it's only a 40-year moving target. But when you think about the issues of it and how you do it, it's going to be complicated. So the future of nuclear power, what do I think? I think really still only in non-democratic societies. A state or a politician is not going to want to tolerate the political risk of a major nuclear incident. And the state is not going to want to underwrite the dollar risk of operating or building and exporting nuclear reactors. So I think building new nuclear reactors is still going to be very difficult in democratic societies. France, Japan, and South Korea, they're closing reactors. They're not building or exporting reactors now. May change somewhat as a result of the Russian thing. India and China are building and exporting reactors. But the real question is Russia is no question is the unrivaled leader in exports. Before the Ukraine thing, there were 33 plants on order from Russia, $20 million each. They offer fuel supply and reprocessing. They have 200,000 people in the industry. And there's no question they were the leader in designing plants, small nuclear plants. This is a Russian ship that has two 50 megawatt reactors on it, which is about the same as the reactor size on a submarine. And it can be taken out to sea, taken next to a city, and hook up the electricity to the city. And they can heat a city, power a city for 100,000 people. So the Russians clearly were the leaders in this technology. What that means and where it's headed, I don't know. In my case, nuclear power will always be expensive, and it'll get more expensive because it gets safer. It'll have political bomb grade uranium 235 and 239 issues. You're going to worry about what you're going to do with the spent fuel. It'll have occasional dramatic incidents. They just happen. Planes crash. They're going to have spent fuel storage and handling issues. The best technology now is they're going to store the fuel forever on the site. So if you've got a nuclear plant in your state, you're going to store the fuel there. It's going to be not understood by 90% of the general public, and it'll be the unexpected, terrifying risk that will be okay for you to take, but I'm not going to take that risk. It's sort of like Montana saying they're going to accept nuclear power from Idaho Falls from small nuclear reactors, but don't put that plant in Bozeman. This is a picture of the plant in California, and it shows this plant may or may not be shut down. This is where the nuclear reactor fuel is stored. You'll see it here. Now, the Palo Verde nuclear station outside of Phoenix is the most efficient nuclear complex in the world. There's 3 operating nuclear reactors that was built 50 years ago. They run at 85% capacity. They're marvelous. You can see the spent fuel containers out here. I think there's no question that plants like this will continue to operate. They're so low cost, and that's just going to continue. So in summary, where are we headed? I think new nuclear plants will be complicated and expensive. And again, I don't think building new plants will be particularly tolerated by democratic societies. Russia, China, and India will dominate new construction. Some existing plants will continue to operate. It's just, they're very efficient. Their capital costs have already been amortized. So nuclear plants like in Nevada and maybe even California are so efficient to operate that they may continue to operate. And it may be possible that some plants will be built on an existing site. Now, can somebody come along and build a fourth site on a plant in Arizona? Could be. Could they come along and put another site on a plant in Iowa? It could be. Nuclear waste will continue to be the Achilles heel. Sweden and Switzerland are the exceptions, and if you'd like to do a little research, I'd recommend that you look up nuclear waste and how it's handled in Switzerland and Sweden. They've had a way to do that. That's what we do here. Is we say we're going to put it in Nevada, and we go through all the work to do that, and then we go to Nevada and say, guess what, we're all done, we want to bring the waste in. They say, we're not going to do it. We're sorry about that. Sweden and Switzerland have come up with a way to be able to politically have places that will accept storage of nuclear waste. And it's an interesting concept to understand. I don't think there's any doubt that solar wind technology will prevail. Battery storage will become very commonplace. The whole technology of batteries is going to change dramatically. Just think about solar. How many buildings out there do not have solar panels on them? If you start putting solar panels on buildings, you don't add anything to the area other than you've got some different kind of roofing, but you've got a whole new way to generate electricity. So I think we're underestimating how that will work. And I think the US in terms of will fall further behind in generation technology as it relates to nuclear. And some of that's the utility structure that we have here. We have 50 states, which is a marvelous system to have, but it's really complicated to get anything done in. You've got these situations where a state can decide that everybody else is fine to have it there, but I'm not going to have it in my state. So it's hard to have a unified approach to things. Utilities themselves are a bit of a problem. We got all kinds of different utility structures. For example, I'm in Connecticut right now, and the utilities in Connecticut will refuse to accept any electricity generated by home solar units into their buyback system. That's different than Arizona, where you can generate electricity from your home solar system and the utility company will buy it from you. That's not true in Connecticut. So the utility structures themselves present a bit of a problem here to us in terms of generation of power. So I'm glad this is over. We've got a few minutes left for questions, and I'll be glad to take some questions. And if people have a lot of questions and it strings out a little bit, that's fine. Okay.
Anyone have any questions? Feel free at this point. You can unmute and ask.
What about, I know the discussion was on nuclear waste, but if we're going heavy towards solar, don't solar panels take a lot of chemicals to make? And then we've got disposal issues, same with batteries.
They do. And I don't pretend to understand that. So I think that's true. The one thing that's different about nuclear waste is, it's harmful because of the radioactivity it gives off. That doesn't mean that waste from solar panels isn't. It doesn't mean that waste from coal plants is not dangerous. So I think that's a valid question. I just don't have the background to be able to understand it or make any comparisons.
A number of years ago, I had the opportunity to tour the Yucca Mountain storage facility. What's its status now? Is it operational?
Well, there are two storage facilities in Nevada. One is for low-level contaminated nuclear material, and that's operational. It's getting filled up quickly, but it's operational. The other one that is not operational is storage of encapsulated high-level nuclear waste. And that was just turned down, I think, a year ago by the Nevada legislature led by Harry Reid. So I don't think there's a process of being able to store high-level nuclear waste in Nevada. I mean, they have a whole system designed to transport nuclear waste. It was very elaborate in terms of it was built. There was really a plan to use that Nevada site, and they spent 40 years and billions of dollars planning on using that site. But when it got down to the Nevada's approving it, they said no. So I don't think that site's operational.
Any other questions?
Gotta get mine so I can see my Montana State shirt.
There's a question. Sherry, go ahead.
When Russia invaded Ukraine, when they were moving across at the beginning, they fired at the nuclear power plant. What were they thinking?
I think they weren't very smart. I think it's I think at the higher level, the Russians are smart enough not to want to get into Chernobyl and start digging holes in the ground and releasing radioactive material. I think that if there's a problem with that, it's at the level where the soldiers don't really understand that. And I think that's just how the chain of command works. You can't expect a soldier that's in there for 90 days to understand the same kind of political risk that somebody else would understand. So, but that can happen. I think it's not unusual that you would have shelling of a site that has nuclear waste and it would uncover more nuclear waste. And I think that's a risk. I think they were smart enough not to involve themselves in the operating nuclear plants in Ukraine. I think they sort of stay away from that. But I don't know where that's headed. I don't think there's any doubt that this whole Russian thing will, over the next 20 years, have a significant effect in terms of how electricity is generated and how it's distributed. And I don't know what that means.
Thank you.
A couple other questions online too. Is there concern using surface or groundwater in Arizona or California to cool plants?
Sure, there's a lot of concerns. Now, interestingly, the Palo Verde nuclear plants outside of Phoenix are cooled by wastewater. They're the only plants I think that exist that do that. That site was built 50 years or so ago. It was built 40 years ago. It was built 50 miles from Phoenix. Now, you're never going to put a nuclear plant today 50 miles away from a major population center like Phoenix. It just happened that they were able to do that. Helped a little bit in that the guy that owned the land was also on the Nuclear Drug Regulatory Commission at the time, and he made a lot of profits by selling the land. So, but the concept of using that wastewater to cool the plants is kind of really unique, and I don't think that's used anyplace else. But sure, there's a big problem in Arizona and that area with using wastewater. I mean, using standard water to cool generating sources. Yes. Palo Verde plant's an interesting plant if you want to do a little bit of research and look up Palo Verde nuclear plant and read the history of it and whatnot. It's worthwhile doing. It's an example of a nuclear plant that's, again, the most efficient nuclear plants in probably the world. And the cooling system is really kind of unusual.
Does the cooling water get radioactive in the process?
No, does not.
I think you kind of just answered one of Pixie's questions here. Anything positive going on in energy generation in the US? What would change this picture?
I'm sorry, what was the question?
She said, is there anything positive going on in the energy generation in the US? What would change this picture?
Well, it's positive in that the government is now funding, they're spending $2 billion to help Bill Gates, excuse me, build his nuclear plant in Wyoming. And I think funding things like that is worthwhile. And I hope they continue to do that. I mean, the Bill Gates of the world, the Elon Musk's of the world. I mean, look at electric cars. Look what one person did with an electric car. I mean, everybody's poking fun of Musk when he got started on this. But the Tesla has revolutionized the auto industry. Everybody in the auto industry now is chasing Tesla. They're spending fortunes to do that. There's an article this morning in the Wall Street Journal about Ford is now laying off people from their internal combustion units because they don't think they'll be needed because of the dominance of electric vehicles. And their Ford truck, Ford F-150, they sold 200,000 units immediately, and they've had to shut down taking orders. So I think one thing you can do is fund people like Musk, Bezos, Gates, because those guys make a difference once they get going. And I guess we're now doing that. So I think that's worthwhile. U.S. doesn't have a long history of funding research for those kinds of things. That's just not our nature. It's a capitalistic society. And that's why the major collider system that was built years ago was going to be built under the state of Texas, and the Texans decided they didn't want to do it because it didn't make any money. So now it's in under France and Switzerland.
Well, this has been so interesting, and I do want to respect your time. I know we're a couple minutes over, but thank you everyone for joining us. And Bobby may have a few words to share as well.
Just in gratitude. Thank you, Thea, for making this happen. For those of you who don't know Thea from South Dakota, OLLI, she's a rock star, and I'm sure you all know that already, but you've been wonderful to work with, and she and her team have single-handedly put this all together. And thanks, Jerry, for your time this morning, or this afternoon in your case, sharing this information with us. It's been highly informative. Even though I've heard this a couple times, I learn something every time. So thank you.
Definitely, and thank you. Please take our survey, and we appreciate all of you. Take care. We'll see you later at our next OLLI Extra.
Okay, thanks a lot for giving me the opportunity to do this.